Bam, Mr. True. In this video, we are going to introduce the geometric figures of segment, rays, and distance. We're also going to be talking about a lot of vocab and definitions about midpoint, what a bisector is, ruler postulate, and what is this? Maybe segment addition postulate. So we have a lot of definitions to cover. So let's get started on our notes. Segment, rays, and distance. So we have a line here marked with 3 points of A, F, and B. And you'll notice that I'm naming the line AB or BA because it extends in both directions forever, so it doesn't really matter what order you use those letters. I could also use, call it line FA as well. But line AB or BA contains F and has a length of infinity. Okay, so lines will extend in both directions forever and thus not really have a measurable length. This is sort of like theoretical maximum length of infinity, which is an idea, but it's not an absolute number. So we can kind of say you can't really measure the length of a line. Whereas if we have this line marked off and just set it with the endpoints of A and B and not have those arrows indicating that it extends forever, it just stops, it's a set length, it starts at A and ends at B, or starts at B and ends at A, segment AB or BA consists of endpoints of A and B and all of the endpoints in between. Now, the difference between having this additional point of F and this one does not is simply when you have a line is defined by 2 points, and this third point of F can be anywhere. It can be between A and B, it can be off to the left of A or to the right of B, because that line extends forever. Whereas with the definition of a segment, we have these set endpoints, and then we can just simply say that the segment consists of those endpoints and all of those points in between A and B. We're not going to just put in a random F and say it consists of that point regardless of where it's at, because the segment is just between those endpoints. Please note again, be careful when you are starting your lessons in geometry and learning about your notation and all this vocab introducing, that you use the proper notation. This is segment AB. It does not include the arrows, the double arrow line that I've indicated above this notation here for the line. Ray AB consists of all points in segment AB and all other points C such that B is between A and C. We have to really kind of, these vocab, these definitions are they sound a little bit confusing. Why is this mentioned F? Why is this mentioned in C? We have to be very specific in our definitions in mathematics because they have to hold true for all scenarios. And it's kind of like saying, how would you define a square? Of course, that's another geometric figure we haven't studied yet, but we know kind of what a square looks like. It's got 4 sides. All those 4 sides are equal. But if I said a square is a 4-sided figure that has 4 equal sides, then there are other shapes. One of them you're going to learn later, called a rhombus, would still fit that definition. So when we say, what is a square? Well, it has 4 sides. They're all straight or linear sides. That it has 4 angles, but all of those angles have to be 90 degrees. They can't be just, any measurement. All the sides have to be of equal length. So what they say here with a ray, this ray AB consists of all points in that segment AB, and notice the segment notation here, but it extends in one direction forever. So all other points C such that B is between A and C. In other words, we have this line segment AB, but now we're going to let it continue forever, and through that extension of the ray in that one direction, we can pick another value, another point of C, such that B is between A and C. So that segment, or that ray, is extending in one direction. Now, as you notice here, when I named this line AB, I'm noting that you can have the 2 points you're using to define the line in any order, A, B, or BA. Same thing with the segment. But a ray has just one endpoint, and then from there extends in one direction. So you do not have an option in how you label or name that ray. If you'll notice here that I have sort of like a single directional arrow, and the starting of that arrow starts with the only endpoint that this ray that I've drawn actually has, which is the A. If, just to really try and drill it home, if I were to draw this ray, and let's just put a D here and an E there, then the only way I could name that ray would be D, E, and then start my little arrow above those two letters indicating, you know, yes, I'm trying to give you the name of a ray, and the arrow starts with D, just like that is the only endpoint of my ray, and then goes through E. Okay, so you do not have a choice in the order of those two points when you give your name of that ray. So here I've drawn a number line, and I've identified 3 points along the number line. We're clearly going to be talking about the mostly about this point B that is at the coordinate of -1 on the number line, and point C, which is at coordinate 3. So length of a segment along a number line is found by the absolute value of the difference of the endpoints, the coordinates of the endpoints. So when we talk about segment BC, notice the, again, straight line, no arrows with it, just segment BC. As a name, it's got that segment notation above it. Well, the length of BC, notice how there's no straight line above there? When you find or state the distance of a line segment, you do not indicate, when you're indicating length, you do not indicate that segment mark above it. So BC, the length of BC, we can see it goes from -1 to 3, and we can count it out. We can start from left to right and go, okay, -1, let's see here. There's a movement of 1, a movement of 2, a movement of 3, and a 4th movement along the number line. So the length of that segment is going to be 4. But for questions that maybe you don't want to go 1, 2, 3, 4, 5, 6, 7, 8, 9. You know, if the length is too long, or maybe there's fractions involved and you actually need to calculate the length, you know, really work it out, you want to take those endpoints or those coordinates. And so I have an endpoint or coordinate of 3 and -1. Now if I do 3 minus -1, I get a length of 4, or I get a value of 4, and that is the length, the distance between those two endpoints. If, however, I do my subtraction in the other order and do -1, the left side, minus 3, well then, -1 minus 3 comes out to be -4. There's no such thing as a negative distance. Think of like a tape measure, you know, those sort of like metal or plastic boxes, and you pull the metal tape out to measure stuff. That starts at 0, and you start measuring the length by pulling that tape out. There's no negative numbers on that tape measure, and you can't make it spool inside of itself. That's not a measurement, at least not for length. So when you start pulling that tape out, you start getting positive lengths, positive values. Well, that has to be true as well when you're doing just calculations on a piece of paper. So -1 minus 3 is -4. We have to take the absolute value of that -4 and get the same answer of 4. So it really does not matter what order you subtract these endpoints, because the absolute value function is going to make sure that your final answer is equal to 4. And I've already made this comment about the notation. We do not need to include the segment notation, we're not supposed to, when we identify the actual length of that segment. So got to pay attention now. We're getting started in geometry. All these little definitions, all these little notations and little marks as we learn how to express ourselves in these geometric terms. Let's get to the next page of notes. Now we're just getting started in our studies of geometry, and I just want to remind you that like any other math class, or any class for that matter, you know, we give you a lot of information. It's going to be your responsibility to organize these vocab words, or these postulates, or these theorems, or whatever, and, you know, really know that foundational information about the class so that you can answer the questions that come down later on down the coursework. So please get in the habit of doing whatever works for you. Just a vocab list, flashcards, whatever. Work on getting into a habit of remembering, memorizing these facts so that they're at your, just, you know, right at the tip of your tongue, and you can use them through the later studies that we'll have in this class, and all of your classes for that matter. Postulates and axioms, what are they? They're statements that we're going to accept without proof. They're going to be sort of core, maybe you want to think of them in common sense or not, but they're just stated as fact, and then we're going to use those, you know, I guess very basic facts, for lack of a better word, to prove more complex ideas later on down the road. The first one being the ruler postulate. The points on a line can be paired with real numbers, or with the real numbers, in such a way that any two numbers can have the coordinates of 0 and 1. My previous example, I had a number line set out. There was a, I just put some tick marks down the line, and I picked one of those tick marks to represent a value of 0. And then as I counted to the left, I went -1, -2, -3, and so on, and then increased, to the right, increase. So 1, 2, 3, 4, and so on. So, you make a number line, you make some tick marks, you identify one of those tick marks as 0, another one is 1, and that sets up your spacing on that number line. You must keep that consistent. If this width is considered from 0 to 1, you can't then go and use the same width and go from 1 to 5. Nor could you do this is 0, 1, and then, okay, let's make that 1, 2, and then this 2, 5, or 2 to 3. You must keep that spacing even through the entire length of the number line, and you'll just put arrows on the end of it to indicate that it extends in forever in both directions. Once this is set up, once a coordinate system has been chosen, we're talking about the number line now, there's multiple types of coordinate systems. There's a rectangular coordinate system, there's a polar coordinate system. Right now we're just talking about a number line. Once a coordinate system has been chosen, we are talking about that number line, the distance between any 2 points equals the absolute value of the difference of their coordinates. This is just a very wordy math definition that explains exactly what I did in my previous example, how you subtract the coordinates and find the absolute value. The segment addition postulate. Okay, if B is between A and C, that just, we're given 3 points along this, well, I was about to say along a segment. We're talking about, I have it marked as the end points of the segment and then some other point in between. So I'm giving you a segment, and we've given a middle point here of B. If B is between A and C, then AB, segment AB, and notice there's no line above it, so we're talking about a distance. Distance AB plus distance BC is equal to distance AC, and these really don't have to be endpoints, just 3 points within a line, and that sort of immediately breaks up a tiny little segment into there. And this length, like if you were to put a 2-foot board down and then a 5-foot board down and put them end to end, we would understand that, well, 2 and 5 makes 7. That makes sense. This segment plus this segment equals the entire length. We're going to start off here with a very easy example. This segment from A to B is equal to 3, and this segment from B to C is equal to some unknown value of x, but yet the entire length is equal to 10. Now, I'm sure that probably a lot of you already know the answer is 7, because we know that 3 plus 7 is equal to 10. We just, can be able to do that addition in our head automatically. And so you might think, well, I don't need to show work for that. Well, you're going to develop into much more complex questions, not only in this book, but in the following math courses that we take. Geometry is, for a lot of you, not going to be the last math that you take and have to learn in your studies to get whatever ultimate degree that you would like. So we start off with these very basic ideas, show you the structure, try and get you to, some students are resistant, try to get you to walk through that structure and that process so that when you get into more complicated questions, you're still able to do them. I don't know your algebraic background, of course. You might still find this one to be fairly easy, but it's certainly much more complex than the green one, and maybe we do need to show some algebra to figure this out. And if this still you can do in your head, we can come up with more complex examples. So let's write out the formula, let's work out the algebra to get this solved, even though we know the answer is already 7, and see that pattern and see that process and learn that process to do more complicated questions we might see in our textbook. So the two segments, the two parts added together to equal the whole. So we're going to have 3 plus x is equal to AC, the entire length of the segment that's made up of these two parts. And this doesn't have to be just two parts, by the way, as the definition shows. I can have maybe 3 segments and have to add those 3 algebraic segments up to equal the whole, but it is defined as initially with 2. Subtract this equation, subtract both sides by 3. We're doing that because I want to undo this addition of 3, or this positive 3 on the left-hand side. I want to move it over to the right. With the 10, we get x is equal to 10 minus 3, which is equal to 7. Then we can just check that. 3 plus 7, yes, indeedy, does equal 10. With my second example here, I have a segment of x, another segment of 4x minus 4. These two segments are being laid down end to end. and touching at point B. And of course, these have to be collinear points. Okay, we're not talking about this being bent. This is, you know, you're being given parts of an overall line segment, and lines are, of course, straight. So these two parts add up to a total length of 36. So this first segment from AB, which is x, plus this segment here of 4x minus 4 is equal to 36. Why am I using parentheses? A couple of reasons. I'm using the parentheses to identify this second term. Maybe I could wrap it around both to identify the two parts that I'm adding to equal the whole. And when you do substitution, and we are substituting x in for the length of AB, and we're substituting 4x minus 4 in for the length of BC, anytime you do substitution, you should get in the habit of using these parentheses. That way that you make sure you follow the order of operations correctly. If there's exponents, you do those when it's appropriate. If it's subtraction, which these are not going to be, you'll remember to distribute that negative sign through the parentheses. It just makes students come up with the correct answer much more often and not make any sign errors. So we're going to add like terms. We have an x and a 4x. Like terms have the same variable and the same exponent on those variables. So when we add like terms, we just add the numbers out front. So 1 plus 4 is equal to 5. So we get 5x minus 4 is equal to 36. We're going to move that negative 4 over to the right hand side. We're going to want to undo that subtraction, so we're going to add 4 and get 5x is equal to 40, and then we want to move that 5 over to the other side, solve for x, and we're going to do that by undoing the multiplication of 5, and so we're going to divide by 5. And our final answer, of course, is going to be x equals 8. Now, if the directions for this question, I knew I was going to talk about it, so I'm going to write directions out. If the directions were to solve for x, well, then we're done. If our directions are to find the lengths of the two line segments, well, this length here is, well, x, and that is equal to 8. This segment here is 4x minus 4. So let's see. 4 times 8 minus 4. I'm taking that value of x and plugging it into my expression. 4 times 8 is 32. 32 minus 4 is 28. And let's see, does 28 plus 8 equal to 36? Yes, it does. I'm also again showing you here that that's how you're going to check your answer. Actually plug the value of x into these expressions and make sure that they do add up to the entire length that is given. I got one more page of notes. Hopefully this is helping, and thank you very much for watching. Let's get to those on the next page. Woo! Hey! Alright, last page of notes. Congruent objects have the same shape and size. So I've drawn 3 diagrams up here. They're all right triangles. As indicated by this little square in the corner, that's a 90-degree angle. Definition that's going to be coming up in the next set of notes, but hopefully you've heard that before. And what I've done here is I've put some single arcs through the corners of these right triangles. The fact that all 3 of these angles have that same single arc in the corner is my way and the textbook's way of indicating for you that those angle measures are of equal length. And then, or equal measure, they have the same number of degrees in them all. And then I've got double arcs through these angles, so they're also all the same measure. So the fact that these angles are all, we have all 3 triangles having a right angle, all 3 triangles having an angle of some kind of measure here, and then this matching third angle, I'm indicating that all 3 of those triangles are of the same shape. Now, a definition coming up later is something called similar figures, which are the same shape but different sizes. So I've effectively sort of introduced another vocab word for you there. But what we want to look at is, while all 3 of these triangles have the same shape, of course only 2 have the same size. So these are our 2 congruent triangles here, and they do not have to be in the same orientation, just the same shape and size. I've got an example here. Sorry for this mark on the board. I have now 3 segments up here. I'm just going to do a couple of, hopefully you find fairly straightforward algebraic examples. There is going to be algebra and geometry, as you saw in my last example, so all those skills you learned last year are still coming through and will still be getting used. So we have segment CD is congruent. That's an equal sign with a little sort of squiggle on top. That is a symbol for congruent. Okay, so segment CD is congruent to segment EF. Now, it is a segment, so they're both the same shape and they are the same size. So if CD, the measure of CD, the length of CD, no line on the top, so it's not segment CD, but segment CD, again, has a length of 5, then the length of EF. Well, congruent figures have the same size and therefore the same, in this case for segments, the same length. So if CD is 5 units long, then EF is 5 units long. No big deal there. It's just, you know, understanding the definition. Now here I've said that CD is congruent to GH. So CD is a length of 5 again, but GH has a expression that describes its length. So did EF, by the way, but I didn't ask you to solve for X. I just asked you for the length of EF. Not that it really matters because it is just X, and X would be 5. But now I'm asking you to solve for X. I'm not asking for the length of GH. I already know that that's equal to 5. And how do I know it's equal to 5? Because we were just told that they were congruent. So, to solve for X, I'm going to take the length of CD, which is also the length of GH because they're congruent, and set it equal to the expression of 16 equals X, or 16 times X squared. So we have, let's see here, 5 equals 16 X squared. We're going to move this 16 over to the other side by division because we want to undo that multiplication there. So we're going to divide both sides by 16. And I'm going to leave myself very good room here. Let me just come over here. And we have 5 over 16 equals X squared. Now we're going to get rid of that power of 2, that square, by square rooting. Square rooting is the inverse function of the power of 2, or squaring. So we're going to undo that power of 2 by square rooting both sides of the equation. The square root, when you square root a fraction, you can do the numerator and denominator separately. All these old arithmetic and algebra skills coming back. So we have the square root of 5 going in this direction. So the square root of 5 is just going to be square root of 5. I'm not going to be happy with decimal answers. Let's practice, you know, using our brain instead of just using a calculator. Square root of 16, though, the denominator, that is a perfect square, and that comes out to be 4. So X is equal to square root of 5 over 4. If we were looking for the length of the segment, we would have to be held accountable to just using the positive answer, because there is no such thing as a length that is negative, at least not in measurement. But we weren't asked to solve for the length of GH. We already knew that was 5 anyway. We're solving for X. Now, when you introduce your own even root to an equation, in this case the square root, when you introduce your own square root, you need to account for both the positive and the negative answer. So it's not just square root of 5 over 4, but it's plus or minus square root of 5 over 4. And then, of course, you know, you want to make sure that this works. So you can take this value and plug it back in here and do 16 times the square root of 5 over 4 plus or negative squared, and make sure that that does come out to equal 5. Square root of 5 times square root of 5 is 5. The square root of 4, or excuse me, 4 squared is equal to 16. And the power of 2, that even power, is going to cancel out the negative number. Negative times negative is positive. So when you work out this arithmetic, you are going to get that answer of 5 that we needed from the original segment, which was congruent to GH. A couple more definitions and we're done. Midpoint of a segment. It divides it into 2 congruent segments. We're just defining the definition. I'm not giving you the formula for finding midpoint. Just the midpoint of a segment is such that it's right in the middle of a segment, and the 2 other segments that it created, basically, like we had the original segment of AB, and then we identified the midpoint, so now we have 2 segments. We technically have 3. We have one here, and then the entire segment of AB. The length of from A to C, AC equals CB. Okay, so we have two different notations. Are you talking about the shapes or are you talking about the lengths? segment AC is congruent to segment CB, or, as I just discussed with the fact that it's just segments and I, for some reason, rattled off length AC equals length CB. Be careful of your notation, okay? Don't use a congruency symbol when you're talking about lengths, and don't use an equal sign when you're talking about segments. Bisector of a segment is a line, segment, ray, or plane that intersects a segment at its midpoint. So in white, I have segment AB. I've got its midpoint here at C, and I know it's the midpoint because I've got a couple of sort of vertical slashes through these two parts. These are, again, sort of a geometry notation here for equal. So segment AC is equal in length to segment CB, and that's indicated by these two little hash marks. I've got plane P coming through and intersecting the line segment at C, so it's a segment bisector. I have line Q that, see how it's solid? I've drawn it solid both to the left of C and to the right of C, so really this line Q is drawn within the plane of P. So line Q is a segment bisector because it goes through the value or the point of C, which is in the midpoint of AB, and then this line segment, which could end at C, I could also redraw it and pass through C, but the line segment DC is also a segment bisector. That is the end of my definition, talking about, what did we talk about in this section? Segment, rays, and distance. The next video is going to be focused more on rays, because if you take two different rays and you make their endpoints equal and have them extend in different directions from that common endpoint, you develop an angle. So in the next video we're going to be talking about angles, and really that will be involving a geometric figure that is made up of two different rays. So, I'm Mr. True. Go do your homework.